Alright, so trying to make a quick video to explain this a little bit better. Hopefully, maybe, visually explain it. So as far as IV infusions, right? When we first start a medication off, we don't have a needle that's primed, right, at the end of the IV tubing going straight into the vein. Usually we plug this into an IV catheter. So for starters, we have medication A, and what we've done is we've gone and we plugged it into this J loop here that is going into our patient. So whenever we start this medication, right, it's got to go through the J loop, through the IV catheter, and then get to the patient. So this area between where the medication is kind of plugged in and where it has its effect on the patient is called our dead space. Right. So with just the one medication, just medication A being on here, that doesn't matter too much because we're only dealing with like 1, maybe 2 mLs. If we go and we plug in or Y site, we're going to have here medication B, right? This is where things become a little bit more of an issue with the dead space. Because with medication B, as it gets plugged in, it now not only needs to go from that line and still through all this, it needs to go through this IV tubing where it's been Y-sited the whole way through all of this, then through the J loop, then through our IV catheter, and finally into our patient. All right. So the dead space here would go to that Y site and then into the patient. That is our dead space. Okay, so now where these two medications mix together, okay, so we have our Y site. This area, because we have a new dilution of Med A, Med B, whatever they're diluted in as well, might be like, D5, normal saline, etc., is all coming together here to go out there and then go into the patient. This area, where those medications are mixed together and then going into the patient, is called our common space. And this is the area that's of concern when we're talking about Y-siting meds. The first aspect of it to understand is the rate changes, okay, or how common space rates work. So for the rate, it doesn't matter if we have our one Y site here, if we had a manifold with a whole bunch of Y sites coming off of it, right? And we add all these up. So we had all of these plugged in. The sum of all of those points to our common space is going to get our common space rate. So in this case, we have Med A is running at 50 mLs per hour. Med B is at 200 mLs per hour. So we'll do 50 mLs per hour plus our 200 mLs per hour. All right, so that gets our rate at 250 mLs per hour. So our common space rate, write this over here, is 250 mLs per hour off the get-go here. So if we have any kind of changes in the rates, that's going to throw this one off, right? The other portion is that if we were to take a needle, okay, we're going to take our needle and stab it into this tubing right here, pull back on our little syringe, and we're to extract some of this, we're going to have a dilution of Med A and Med B. The way we figure that out, okay, is we take our rate, divide that by the common space rate, and then multiply that by our dilution. So what I'm saying is, in this case, we have the 250 mLs per hour rate, okay? So we'll do the 250 mLs per hour. We're going to start with Med A. It's going at 50 mLs per hour. So 50 mLs per hour of this 250 solution is 20%, or 0.2. So 20% of our original dosage here, which is our 1 milligram per ml, in this case would come to the 0.2 milligrams per ml, is what the dilution here, if we pulled this medication, is. Okay, so our common space dilution has 0.2 milligrams per ml of Med A. If we go and do the math, we do the same to 200 out of 250. Multiply that by its dosage is the 1 milligram per ml. That'd be 0.8 of Med B. 0.2 milligrams of per ml A and 0.8 milligrams per ml of B, right? So now if we do any kind of rate changes, that's going to jack this all up. Okay, so we use the same formula, the same idea to kind of figure out what kind of change we're going to have. So let's say Med A is running, and then we come over and we stop medication B. Okay, so our initial column space rate was 250 mLs per hour. Medication B is still in this area. It's still mixed into the common space. So even though it is stopped, that change, again, that dead space area, right? It's not going to have a direct effect because it's still going to be getting pushed through by Med A. Okay. The other issue is that now we went from 250 mLs per hour. Now just Med A is running at 50 mLs per hour. So even though the initial dosage, right, was able to balance out, if we multiply this, the 0.2 times 250, it's the 50 milligrams per hour, right? Now if we change this up, we change up the rate. So now we got 50 times what is now 0.2 milligrams. So we got 50 mLs per hour of our new rate times the 0.2. Okay. Let's see, let me plug this into a phone. So we're coming to 10, right? So that's now 10 milligrams per hour when our ordered dosage, or the amount that we want going in, is 50. And it's, again, it has to clear this dead space. So until this dead space is cleared, this patient's getting a dosage of 10 milligrams per hour rather than 50. Okay. So if we were to do this the other way, and we were to cut off Med A, okay, so we went from 250 to now we're going just 200 because it's just Med B going. We do the same thing. We'd multiply that dosage. So medication B, that should be getting 200 milligrams per hour. We'll multiply that times our 0.8. And we're getting 80% of the dose, or 160 milligrams per hour, if we were to cut this one off, instead of 200. This can play a pretty big issue for a couple reasons. One, let's say if this were epi, right, and we go and mess with the dosage here, it's not going to have the effect you want until the dead space is cleared, and it's going to have a different effect because of this dilution going through here until that's able to catch up, right? So if we were to, let's say, double the rate of Med B, right? We had this one going through. So now we're going at 400 mLs per hour. We'll do the same thing. So 400 plus the 50. So we're going 450 mLs per hour. We still have this same dilution here. So Med A, that was initially getting the 50 milligrams per hour. That's 450 times our 0.2 times 0.2, 0.2 if we want to be fancy, is 90 milligrams per hour. That's almost double the dosage that we want this patient to be getting. And they're going to get that until, again, that dead space is cleared. Other issue, if we do have a whole bunch of medications here, all string-lined, and they're all interacting with each other, the one thing we kind of forget about when we have these nice manifolds that are running off to the different lines is the sum of these all together is what our common space rate is. So if we had 5 medications running at 200 mLs per hour, our common space rate would be 1 liter per hour. That's a lot of pressure that you're putting onto this IV catheter in the vein. That can cause catheter whip. It's going to agitate the vein more, and it can cause the vein and everything to blow out better, or faster, sorry. Another way to explain this, right, I like to take the analogy like we have a treadmill, right, and if we have somebody who's dropping little, like golf balls off on here, right? He's dropping a golf ball, and if you can imagine that this is going at whatever speed this way, okay? Now, originally, if it's going at whatever speed, this isn't going to matter. It's just going to kind of trickle this way. If he goes and he wants to change things up, let's say he was doing 1, per minute of that, and he wants to drop another one at 1 per minute. Now this is going to drop, and it's going to take a while until these catch up. So until then, for him to make room, he's going to have to speed this one up. So instead of getting 1 per minute of these red balls, he'll get like 2 per minute, right? Until this is able to balance out. And now we have a 50-50 dosage. Now, if we were to stop that, let me erase here. If we're to stop it, it's going to take a minute for this to catch up and for these to all be replaced by the red balls being dropped off. Okay. So it's the same thing going on that way. And that's actually quite literally how I usually think about it in my head. It's just kind of replacing those like that going down the line. But that's why it's important to understand this, just because of that difference in that dead space we discussed in the common space. So that common space is our big area. So I'll just write this down on another one. Let me clear all these just to make this nice and pretty. So we have our line, and we have, in this case, is our patient. We have our first one here. Next one. So this initial area, okay, that's filling in from med A is our medication line. It's going to keep going on through here until it gets to our patient. That area between here, which is our J loop. So if we were to say this is the J loop and the catheter going to the patient is dead space. If we were to take here and Y site another med into it, med B into this one, and then it's going to go this way, is our dead space for that medication. And it's going to extend to there. And then we have where those two mix together. So we have our other color going through here is our common space. Okay, so hopefully that makes things make a little bit more sense with it being drawn out and explained. If not, again, feel free to reach out for questions. Hopefully that clears things some stuff up, and you can apply that a bit better for your practice.